This is question 21 from the SACE Stage 2 Physics Course Companion from subtopic 3.2 Particle Wave Duality. Here we have an experiment similar to the Davison-Germer experiment. Electrons are being accelerated through 70 volts. These electrons are instant upon a crystal iron structure, and they're found to scatter at an angle of 16 degrees. What we need to do is use our diffraction grating formula to approximate the spacing between the ions in the crystal. Now, before we start calculating this spacing, it's probably worthwhile going through the steps and the concepts that we need in order to work this value out. So first, it's probably easiest to work backwards, that we're thinking about the diffraction grating formula. M lambda is d sine theta. We're trying to calculate d. Therefore, we need the wavelength of the electrons. In order to find the de Broglie wavelength of the electrons, we need the speed of the electrons. In order to find the speed of the electrons, we need to calculate the energy of the electrons. And that's where we start. So our first step is using the relationship that work is equal to the, moving around a little bit, that work is equal to change in energy, which in this case is Q delta V. Our second step would be relating this energy, Q delta V, to kinetic energy, which is equal to half mv squared. So we'll calculate Q delta V, rearrange this to get the speed of the electrons. Then we'll use the de Broglie relationship. Momentum is h on lambda. Substituting P equals mv into this, we have mv equals h on lambda. Therefore, lambda equals h on mv. And then finally, we'll use the relationship m lambda equals d sine theta to calculate d, which will be our approximation for the spacing between the crystal ions. So there's quite a lot going on in this question. It's a fairly complicated question. There's lots of different things which are needed in order to get to your final answer. Yeah, it is complicated, but it's fine. Once you go through all these steps and sort of map out where you want to go, it's actually not too bad. So let's dive right into it by first calculating Q delta V. So here we have Q delta V. Q is the charge of the electron, so that's 1.6 times 10 to the power of minus 19. Our potential difference from the question was 70 volts. And if we substitute that into our calculator, we get 1.12 times 10 to the power of minus 17 joules. Next, we are equating this to our expression for kinetic energy and rearranging for V. So here we have EK equals half mv squared, which we rearrange so that it's V equals 2 times the kinetic energy divided by m all square rooted. Now we can substitute our values. So 2 times our energy from before, which is 1.12 times 10 to the power of minus 17, all divided by the mass of an electron, which is 9.11 times 10 to the power of minus 31, all square rooted. And if we calculate that, we get 4.96 times 10 to the power of 6 meters per second. Now we are using our de Broglie relationship from up here, so we have lambda equals h on mv. H is Planck's constant, so 6.63 times 10 to the power of minus 34 divided by mass of an electron, 9.11 times 10 to the power of minus 31, multiplied by the speed that we've just worked out, which is 4.96 times 10 to the power of 6 meters per second. I don't need to write that here. And if we put that into our calculator, we get 1.47 times 10 to the power of minus 11 meters. So finally we have the de Broglie wavelength for the electrons. Our last step, m lambda equals d sine theta, therefore d equals m lambda divided by sine theta. In this case, since m's the first maxima that's observed, that's just 1. Wavelength we've just worked out, 1.47 times 10 to the power of minus 11. The question gives us the angle, which is 16. So put that here. And when we substitute all of that into our calculator, we get 5.32 times 10 to the power of minus 10 meters. And that's it. So that was a fairly long and complicated process. If you ever come across questions like this, I think the best way is to map out what you're trying to do at the beginning, like we've done here. Work backwards from your answer to essentially what you're given in the question, and then you can see what you need to do, what you need to calculate, and then it becomes significantly easier than just trying to dive in without any real plan. Yeah, I hope you enjoyed that. It's a good, complicated question, really interesting one about particle wave duality, and yeah, and it's all very much experimentally verified. It's not something that's made up. And that's it.